Alright, so in this video we're going to be going over binary trees. So we're going to be covering briefly the binary tree data structure and how it's defined, and then we're going to be going over an implementation of a binary tree in Python. So for definition, a binary tree is a tree data structure in which each node has at most two children, which are referred to as the left child and right child. So here is an example image of a binary tree, and each of these circles here, these are what we call the nodes of the tree. So just like in a linked list, we had that the nodes in a linked list stored some type of data. So this could be an integer, it could be a string, it could be a pointer to another data structure. In this case, these nodes contain integers. So unlike a linked list where the node pointed to the next node in the list, a binary tree has two pointers that point to its children. So every node in this tree will have at most two children, and this makes traversing such a data structure interesting and a little bit more varied than you would a linked list, and we'll get to that later in this video. So a bit more terminology about a binary tree. We refer to this top node here as the root. So in this case, the node that contains the element 2, this is the root of the tree. And then the left and right children of this root node are the nodes containing 7 and 5 respectively. So they are the left and right children of 2. So if we consider this node here, this node that contains a 7, it also has at most 2 children. So its left and right children are the nodes containing 2 and 6. And we say that 7 is a parent node with respect to 2 and 6. So 7, this node here containing 7, is the parent of the nodes containing 2 and 6. And likewise, this node here containing 2 is the parent of 7 and 5. So as we go up the tree, we go up kind of the family tree, if you like. So 2 here is the grandchild of 2. So 2 is kind of the grandparent, parent, and child. And you could keep going up the tree. We just refer to 2 as an ancestor of 2 down here. So a few more pieces of terminology here. We refer to the nodes, the very bottom of the tree, as the leaves. So the root is up here and the leaves are at the very bottom. We can refer to the depth of the tree. So if we start at the top here at the root, and we keep going down, we keep a count at how deep, how many levels we've traversed down. So for instance, this root here is at level, let's say you can start at 0 or 1. And then as you go down, these nodes here are at the next level. So they're at level, let's say 1, 2. And then as we go down further, these nodes 2, 6, and 9 are the next level down. So they're at depth 3. And then these nodes here, these leaves, they're at depth 4. So 1, 2, 3, 4, depth 4. Count from the bottom to the top, and that will give us the height. So if the leaves are the bottom level, let's say height level 1, then we can go up to the next level up here. These nodes are at level 2, level 3, and then level 4. So this tree has height 4. So there's different types of binary trees, and this list is not complete. There's plenty of other types of binary trees you can consider, but we can consider 2 that we're just going to mention on this slide. So a complete binary tree. So this is an example of a complete binary tree, and a complete binary tree is one where every level except possibly the last is completely filled and all nodes in the last level are as far left as possible. So this level is completely full. You can only have one node here. This level is completely full. This node has the maximum amount of children. Both of these nodes, they have the maximum amount of children as well. And then all of the nodes in the last level with the leaves, it's not full. So we have here in the definition that possibly the last level is not completely filled. And also the last level nodes, the leaves are pushed to the far left. So this node is as far left as you can go. So in order for this to maintain the property of being a complete binary tree, the next node that we would insert would have to be the right child of this node 4, and so on and so forth. So a full binary tree is sometimes referred to as a proper or plain binary tree, and this is one where every single node has either 0 or 2 children. So every node in the tree has 2 children except for the leaves, which have 0 children. So this is full tree. Every I guess space in this tree is being taken advantage of. So this is a full binary tree. So with that, we have enough terminology and information to start defining the data structure of a binary tree. And we're going to see a lot of overlap with what we saw when we defined the data structure of a linked list. So I would recommend that if you have not gone over that series, or if you need to brush up on linked lists, especially how they're defined, let's say in Python, to get a flavor of how we're going to extend on that, I would encourage you to go over and check out that series of videos, maybe the first couple of videos, just to get a flavor of how one would define such a data structure. And once you feel comfortable with that, we'll go over to the terminal and we'll start to define a binary tree. All right, so let's go ahead and code up our binary tree data structure. In order to do that, we'll first define a node class. So this is going to be really similar to what we did when we defined the linked list data structure, where we had a node class as well for the nodes in the linked list. So we'll say class node, and then let's go ahead and define the constructor for this class. So we'll say def init, and just like for the constructor of the node class for a linked list, it's going to take self as it's a member of this class, and also value. So this is the type of value we wish to store in this particular node. So we'll set the class variable value equal to what's passed in here. And then unlike a linked list where we had the class variable of next set equal to none, we're going to have left and right equal to none. So next that was the pointer that pointed to the next node in the linked list. Here we're going to have two other pointers, left and right, which are going to point to the left and right children of the given node respectively. So we'll say self.left is equal to initially none, and then self.right is equal to none. So pretty similar to what we saw in the linked list class, with the exception of those two last variables. Let's go ahead and define our binary tree class. So here what we're going to do is we're also going to define our constructor. So it'll take self as it's a member of the class, and also root, as that will define the tree. So we'll say self.root will be equal to node of root. So what I'm doing here is I'm assuming that a value, like let's say a string or an integer, will be passed in to define the binary tree. And then what I'm doing is I'm setting the class variable self.root equal to a node of that. So we're converting whatever data is passed in, we're storing that into a node, and we're setting that as the root of our tree here. So that's pretty much all we need to get started. We can actually start filling this tree up, although we won't be able to print anything out at the moment. So we can say tree.root is equal to, let's say, or actually first we need to define a binary tree object. So we'll say, let's say binary tree, or we'll even be a bit more concise here. We'll say tree is equal to binary tree. And in this argument, we're going to put in the initial value of the root. So we'll go ahead and put 1 in there. So we have a tree object now, and what we can do is we can start filling in the nodes, the left and right children of this particular root. So what we can do is we can say tree.root.left is equal to node of 2. So what this is going to do is we're going to start off with our root node here. So 1 is the root of the tree. And then what we're doing is we're creating, let's see if I can get the right slash. So we're creating a left child of this root node, and we're setting the value of that equal to 2. So we can also create a right child of the root node. We can say tree.root.right is equal to node, oops, didn't mean to do that, is equal to node of 3. So here what we can do is we're going to define the right child to this thing. We're going to set that equal to a value of 3. And we can keep going. So we can say tree.root.left is equal to node, let's say 4. So what that's going to do is it's going to define, let's get some more space here. Move this over here, move this over here. A bit more space there. So let's see, let's just space these apart appropriately. So 2 is the left child of the root 1, and then 2 is going to have a child now. So 2 is going to have a left child. Let's see here, move this down here. So 2 is going to have a left child of 4. And then we can also define, let's say tree.root.left.right is equal to node of 5. So what I'm doing here is I'm saying that tree.root.left, so here we're here, .right, so right will be the right node of 2, so we can set that equal to a value of 5. Like that. And we can continue in this way. So if we want to insert nodes in a tree in this way, this is kind of what this particular tree is going to look like in this case. So we can go ahead and fill this in a little bit more. So I've gone ahead and filled in the tree to be a little bit more complete here, adding 2 more nodes of this node right here. So I've added a left child and right child for this node here. So I've just filled in the tree a little bit more, not necessary, but it gives us a little more data to play with. So now what we want to do is we want to find some way to actually go through the tree, to traverse it in some way, and to actually print out the elements stored at the respective nodes. So Remember, for a linked list, there was pretty much just one way to traverse it. There was a linear way. We just started from the front of the list, and then we just moved progressively through the list. Sometimes you might do something fancy with maybe 2 pointers, where you have one pointer that kind of goes a few nodes ahead of the first one, and then you kind of traverse it using 2 pointers, but you still traverse the list in a linear fashion. So here with a tree, since we have a different type of structure, we're going to think about the different types of ways one can traverse a tree, and we're going to be going over kind of the most basic ways in which one can do that, focusing first on something called depth first search. And there's 3 different flavors that we'll be covering, which are pre-order, in-order, and post-order traversals. So we'll be covering those, and then we'll be seeing how we can implement each of those traversals in Python. And if we consider a recursive way of defining each of those traversals, then once you define one, it's pretty straightforward to define the remaining 2. So we'll cover that next. So back to the slides. As we mentioned before, a tree traversal for binary trees here will be a process of visiting, checking, and or updating each node in a data structure exactly once. So as mentioned before, unlike a linked list or any other one-dimensional data structure like an array, which are traversed in a linear manner, trees can be traversed in a number of different ways, and we're going to be going over some of those. So we're going to be focusing first on depth first search, and those 3 different ways that we mentioned, post, pre, and in order traversals, will be flavors of depth first search. And as I mentioned, I guess this is just kind of a reiteration of what I mentioned before. There are a few common ways to do so, and the depth first search order that we'll be considering are these 3 different types of ordering traversal schemes. So let's first cover pre-order traversal. So what we do here is we start at the root. We check if the root is empty, and then we just kind of go down through the left subtree, and then we go back up, and then we consider the right subtree. So let's actually just follow kind of how pre-order traversal goes. So we start here, we start at the root, and we print out the element at the root. So that's going to give us our first output of the pre-order traversal here, this F. So then we move down the left subtree. So we're here, we're at B, and so we print out the element at B. That gives us a second element here. And so then we check if the left node of this one is not null. It's not, so we follow it here, and then we print out the element at that node, which is A. And so then we check the left, we check if there's a left node of the one that we're on here. So there's no left node here, so that's null. So what we do is we go back up to this node here, this B, and then we check the right now. So we move down here to D, this node here with D. We print that out, so now we're at D. And then we follow the left subtree. So we start here, we're here now at D. We follow left, we see that we're at C now, print that out. We check if there's a left node here to C, there's not, it's null. So we move back up to C, we move back up here to D, and then we check the right subtree of D. So we move down here to E, print that out, check left, nothing, check right, nothing, move up, move back up to the root. We've already covered that, so now we move to the right subtree. So we move down to the right subtree. We're at G, we print that out there. We check if there's a left node. There's nothing there, so we don't do anything there. So we check if there's a right node. There is, and that is I, so we print out I to the screen. And then we check if there's a left node. There is, it's H. We go ahead and print that out. We check if there's a left node. There's no left node. Right node, no right node. Go back up here to I. Check if there's a right node. There's nothing. So then we move back up, and we're done. So we've got our pre-order traversal there. So what we're going to do is we're going to code this up, and then we're going to go back to cover the other 2 traversal algorithms, and those are going to be very similar in terms of implementation from a recursive standpoint. And once we understand this one, implementing the other 2 should be pretty straightforward. All right, so now we're back here in the code. Let's go ahead and create a pre-order print function, which will be responsible for printing out the nodes in a pre-order fashion. So we'll say pre-order print. It'll take self since it's a member of the class. Start, this is the node that's going to be updated on every single recursive call of this function. And then traversal. This is going to be a string that will print out to the screen, and we're going to essentially update this on every single recursive call, and then we're going to return this. So we, at the end of the day, once we're done finishing this function, we're going to have just one string of elements, which are going to correspond to the elements printed out in whatever traversal we specify, in this case the pre-order traversal. So hopefully that will become clear as we implement it. So again, just to kind of clarify the order in which pre-order goes, it starts off at the root, it considers the left subtree, and then it considers the right subtree. That's kind of the flavor of preorder traversal. So we're going to check if the node that we're given in this recursive call is none. So if it's not none, then what we're going to do is we're going to say traversal. Again, this is just going to be a string that will constantly update on every call. So we'll say traversal plus equals string start.value. And then what we're going to do just to kind of separate the output is just add this dash. So on every recursive call to this function, as long as this node isn't null, what we'll do is we'll say, okay, print out the value, concatenate that to this traversal string, and then print out that value and then just append on a little dash to show that we're kind of chaining these outputs together. So it just formats it a little bit nicer. And then what we're going to do is we're going to say traversal is equal to self.preorder print. So we're recursively calling this function, and then we're going to call it with the left subtree, right? So the left child of the node that we're given in this recursive call, and then we're going to pass it in the traversal string that we're going to continue updating on each recursive call. And then once that finishes for the left subtree, we're going to consider the right. So we're going to say traversal is equal to self.preorder print start.right, and then we're also pass it traversals that will get updated on each recursive call. And then once that is completed, we'll return traversal. So let's go ahead and create kind of a helper function, which will be called print, and that will be responsible for, or let's call it print tree. This will be responsible for printing out the tree, and we'll specify what type of traversal algorithm we want to print the tree out in. So we'll say print tree, print tree, so self, and then we'll specify a parameter called traversal type. So here we'll just be giving this function a string. So for instance, maybe we want to print out preorder, postorder, inorder. In other videos, we'll see iterative flavors of these algorithms. We might want to print them out in other types of traversal algorithms. So we'll just go ahead and say traversal type is a string parameter that we will specify to a call to this function. So we'll say if traversal type is equal to, let's say, preorder, then what we'll do is we'll call the preorder function. So we'll say return self.preorder print, and then we'll pass it in the root of the tree because that's where we're going to start the preorder traversal, and then we'll initially pass it in an empty string. So this empty string on the first recursive call will be nothing, and as it goes through this function, it will continually be updated with the values stored at each of the nodes as we follow this traversal. So that's pretty much all we need for the preorder traversal function. So let's go ahead and go down here, and we'll say tree dot print tree, and then we'll specify the traversal type. Again, the type that we specified is preorder. And then maybe what I should do up here is I should also say if otherwise, let's say we feed in a traversal type that's not supported, we'll say, print traversal type, let's say string of whatever you fed in, traversal type is not supported. So just in case someone feeds in some argument here that's not supported for this particular traversal type, so we'll just return false there. Okay, so that was just a bit of error checking, I suppose. So what we're going to do here is we're going to call this print tree function, and we're going to specify that we want to print out the nodes in preorder. So let's go ahead and save this, and what we'll do is we'll clear the terminal, and then we'll say python binary tree.py. And I think I don't see anything because I need to print what is returned from this function. That would explain that. So here we see that the preorder traversal is 1, 2, 4, 5, 3, 6, 7, 8. So let me just copy this, and we'll step through the tree to make sure that actually makes sense. So let's go up here. I'm just going to put that in a comment. Let's see, let's do here. Right, so that is the preorder traversal. So again, we start at the root, that makes sense. So we print out the element at the root, so that's what we do here for the first element there. Then we follow the left subtree. So the left subtree, we've got 2, that makes sense. We follow the left subtree again, we got 4. We check if there's any left node here, there's not, so we move up, and then we check if there's a right subtree here. There is, so we have 5. By the way, when I was back down here, we check if there's a left subtree, there's not. And then we check if there's a right subtree, there's not. So we move back up to here, just to clarify. Check the right child of 2, so that's 5, that gives us 5 here. Check left, nothing. Check right, nothing. Move up, and then move to the right subtree. So that gives us 3, and then we check the left, that's 6. Check the right, or well, check the left here, 6, check left, check right, nothing, nothing. Go back up to 3, check right, we got 7. And then it looks like I just forgot to add in this figure here, this 8. So I'm just going to go ahead and, if I was to remove this 8 here and remove this 1 right there, this would be accurate with this comment here. I just forgot to reflect that in the figure here, in the commented figure. So if we went ahead and just ran this again, just to be clear, the 8 is no longer there. I just wanted to accurately represent what is represented in this comment figure here. So that seems to have given us the preorder traversal of the tree. So that seems to have worked as expected. Good. So let's go over the other traversal algorithms, so postorder and inorder, and they're going to be very similar to what we've seen so far. Okay, so just like we had the preorder traversal, we have the inorder traversal here. And we're going to be stepping through it in a very similar way. So preorder was, we've considered the root, then the left, and then the right subtree. So in inorder, we're going to be considering the left, the root, and the right. So it's kind of a natural name for such a traversal because we're kind of reading the tree from left to right, right? In inorder traversal, left, root, and then right. So if you actually just read off the nodes here from left to right, A, B, C, D, E, F, G, H, I, that is the output of what would be an inorder traversal. You're kind of reading the nodes from the left to the right, and that's going to give us the output of this inorder traversal. So let's step through it in the same way here. We start off with the root, and then basically what we do is we go down as far as we can to the left. So we start off here. Can we go to the left? Yes. Okay, we go here. Can we go further to the left? Yes. So we're here. Can we go further to the left still? No, we can't. So go ahead and print out A. So we print out A. We move back up. We print out B. And then let's try and go down as far as we can here. So we go down. Can we go down further than here? Yes, we can. Can we go down further than here to the left? No, we can't. So we print out C. We move back up, print out D. And now let's see how far down the right we can go. So we go down here to E. Can we go to the left? No. Can we go to the right? No. So go ahead and print out E. So we print out E, move up, move up, move up. And then here we're at the root. So print out the root. So again, left, root, right. So print out the root. And then now we're going to traverse the right subtree. So move to the right, print out G, and then move to the right again. Right, so you're back up at the root, you print that out, and then you consider the right subtree, so you move to the right, and then you check, can you go to the left? No, you can't, so you go up here, you print out G, go to the right here, and then what you do is you say, can you go to the left? Yes, you can. So you're here, go to the left. No, you can't. Print out H. Go back up. Can you go to the right? No, you can't. Okay, so print out I, and then move back up, and that is the inorder traversal. So that's pretty much it for that. So now what we can do is we can implement this. Again, it's got kind of a natural recursive flavor to the way that you would think about how to implement this, especially in a binary tree like data structure. So let's go ahead and go back to the code and implement an implementation of inorder traversal. All right, so now we're back here in the code. So let's go ahead and create another function, which is going to be similar to preorder print, but it's going to be called inorder print. So we'll call this inorder print. So it just will take the exact same parameters, self, start, and traversal. And then in this case, what we have again is we have left, root, right. So that's kind of the way in which the nodes are going to be read off in an inorder traversal. And we'll have a very similar start here. So we'll say if start, so if the start node is not null, what we'll do is we'll consider first the left subtree. So we'll say traversal is equal to self.inorder print, and then we'll say start.left because we're considering the left. And then we'll feed in that traversal. This traversal is going to be the string just like it was in the preorder print that we're going to be continually updating on every single recursive call. So once we've considered the left subtree, go ahead and print out the root. So we'll say traversal plus equal string start dot value, and then we'll say give it a little bit of a dash there for nice formatting. And then what we'll do is we'll consider the right subtree. So we'll say traversal is equal to self dot inorder print, and then we'll say start dot right traversal. Okay, so that's what we need there, and then we're also going to return traversal. Let's go back up to a print tree function here, and we'll add some support for the inorder traversal. So we'll say else if traversal type is equal to inorder. Then what we'll do is we'll return self.inorder print, and we'll pass it the root of the tree. And then again, just like we did before, just an empty string to start us off for the traversal output. So we've got that. Let's move on down here. And if we've got in-order traversal, what we should see is we should see 4, 2, 5, 1, 6, 3, 7. So again, it's an in-order traversal, left subtree first, then the root, then the right subtree. So what we should see is we should see 4, 2, 5, 1, 6, 3, and 7. So let's go ahead and run that to verify that is what we see. I'm going to comment out this line here for the preorder traversal, and then I'm going to go over here and type in order. So we'll write that and we'll give that a run. So indeed we see 4, 2, 5, 1, 6, 3, 7. So that is the in order output of the nodes for an in order traversal. So the nice thing is when you define these recursively, look how similar this preorder and in order definitions are. And indeed for postorder, it's going to be a very similar type of extension from these two functions. In a postorder, you can probably imagine we've considered here the root left right, or left root right. And now for the postorder, I'm just going to go ahead and define the prototype because it's going to be very similar to what we've seen so far. I'm going to say postorder print. Again, it's going to take the same type of information, the same type of arguments that the previous two functions did. And then here what we're going to do is we're going to start at the right. Oh, sorry, not the right. We're going to start at the left, and then we're going to move to the right, and then we're going to move finally to the root at the very end. So I'm just going to go ahead and copy this here, since this is going to be nearly identical to the post-order traversal of what we want here. So instead of these lines being in this order, since we want the root at the end, we'll take this, move it down to the third line here. So we've processed the left subtree, we've processed the right subtree, and then the root. So this is going to be the post-order traversal for this particular tree. So we'll go ahead and see how that looks like. So again, what we're doing here is we're considering the left, the right, and then the root. So it should be 4, 2, 5, 6, 3, 7, 1. So let's go up and create a helper function here for or add some support for the print tree function. So we'll say else if traversal type, if that's equal to postorder, we're going to return self.postorder print of tree.root, and then again an empty string just because that's what we want to start off with. So let's go ahead and run that. So again, just like before, I'm going to comment this out, and then I'm going to take this, modify it slightly, and put in postorder here. So I'm just going to postorder, write that. Let's give it a run. So we see 4256371, 4256371. So that is the post-order traversal of the tree. So that pretty much does it for this video. So just to review, we went over the binary tree data structure, and then we went over the 3 different, I guess, most popular or well-known types of traversals for a binary tree. So preorder, inorder, and postorder. So these are all flavors of depth-first search. And we'll be continuing to investigate this data structure in further videos in this playlist. And for instance, thinking about how to implement these functions not recursively, but also iteratively, and just other things that we can ask, other questions that we can ask about a binary tree data structure and maybe what it can be useful for. So thanks again for watching. The code, as always, will be available on my GitHub page, and the link for that will be in the description to this video. If you have any questions or comments or clarifications or anything like that, do not hesitate to leave them in the comment section below. Thanks again for watching, and have a great day.